Okay, good afternoon. Can you hear me clearly? I'm not too loud? Yep, awesome. I believe we're running a few minutes late, so you're probably just going to remember me as the guy who ruined lunch for you, but I'm still going to put a little bit of effort into my introduction. My name is Benjamin Encz. I'm a software engineer at PlanGrid in San Francisco. It's a blue icon over here. We work on mobile software for the construction industry. And in the last year, I've been also a little bit more active in open source software. You can see the orange icon. That is a project called reSwift that I've been working on. Today I want to talk about leveraging Swift's type system. And the goal of this talk is really to break down things I learned in the last 2 years into a toolkit that I think is useful to a lot of Swift developers. So I don't want to talk about the theoretical nature of the type system, but I want to show you some tools that you can use and that have improved my code and hopefully will improve your code as well. The talk itself breaks down into 3 major components. Firstly, I'd like to go a little bit into the history of types. Why do we have type systems in the first place? What role do they play in our programs? And I think it sets the stage for the rest of the presentation. And then after that, I want to talk about 2 practical sections. The first one is how can we use types for correctness checks in our programs? And that's an area we've all looked into quite a lot since working with Swift. And how can we use types for documentation? So how can we write code that is self-documenting based on types that we use? And lastly, this section, the third one, is a little bit different, where I want to dive into how we can use types to aid our code design. How can we use protocols and generics instead of subclassing? So let's dive into the history. The easiest way to do that for me was to go back to a time where we didn't have types. So right behind me you can see Margaret Hamilton. She was a lead software engineer on the Apollo 11 mission that sent people to the moon. And frighteningly enough, this code for the space shuttle and everything else was written in assembly. And assembly doesn't have any types, which is one of the reasons that it's really horrible to write, in my personal opinion. So what you have to do when you write assembly is you have to remember which bits did I put into which register and which piece of memory. And when you read that, then you have to remember yourself the encoding of the data. So what a type system does for us today, in assembly we had to do that manually. And it also results in code that is really bad to read. So you probably can't read a snippet here, but it's an original snippet from the original code, and it contains more comments than actual code. Because the code itself is so close to the machine level, it doesn't express any intent of our program. So everything has to be documented separately. With richer type systems like Swift one, we can actually express a lot in the type system and reduce the need for comments and such verbose code as you can see here. So today we write code in higher level languages, and types are actually an essential part of higher level languages because they enable the compiler or the interpreter to generate the machine instructions from our code. And for that, the compiler needs to know which types you're using. So this here is a very, very simple example from Objective-C. All we're doing is we're using 2 local variables of type int and assigning them to each other. But even here, the compiler relies on type information. It knows how much space will I allocate on the stack, how do I move these bits between these 2 variables, it will check do they have the same size. So it does a lot based on this type information. And another side effect of languages that have a static type checker is not only that the compiler generates machine instructions for us, but it also does some basic verification. So it will check, can I actually generate code that makes sense given the types that you have annotated in your code? And even Objective-C had some basic type checking built into it. So in this case, this line would compile, but in the next slides I have some examples where the compiler would emit warnings or errors. In the first case, very trivial example, I'm creating an NS number, and then I'm creating an NS string pointer, and I'm assigning the 2 values to each other, and here the compiler will emit a warning. It will say, you're assigning a number pointer to something that is a string pointer. It seems very unlikely that you actually want to do that, because any operation you're going to do after this is very likely going to fail. And the second example is another feature that Objective-C provides. It actually checks if types implement certain messages that we want to send. So in this case, we have a string, and we want to try to call viewDidLoad on it. And Objective-C will see there's actually no method called viewDidLoad on string, so it will not compile this. It will stop us from doing some very basic mistakes. But the Objective-C type system is very limited in the way of things it can express, and therefore it can only catch a very limited amount of issues at compile time. Much more issues will actually show up at runtime. A classic example that you probably ran into before is that we cannot have nil values inside of dictionaries. But a compiler doesn't, you have no way to express that for the compiler. The type system doesn't understand what nil and what nullable is. They're like the new annotations that we have today in Objective-C provide some type hints, but are not actually part of the Objective-C type system. So there's no way to express that we are not allowed to put a nil value into a dictionary. And therefore, we can write code like this, where we just create a nil value, we put it into a dictionary, the compiler will generate machine code, but as soon as that code runs, our app will crash. And that's something we experience a lot in Objective-C. We have some constraints that we actually know at compile time, but the type system does not allow us to verify them statically, and therefore we crash at runtime. So in general, what does a type system do? It really does these three general tasks. For each type, it defines a set of values that are possible for that type, a set of operations that are possible, and typically also a representation. And the richer the type system is, the more we can constrain these definitions. The more we can get to a point where the compiler understands a lot about our program and can verify a lot at compile time. So far I talked about Objective-C, and if you've written both Objective-C and Swift, then you're pretty aware that the Swift type system is a lot more expressive than the Objective-C type system was. So in this section, I want to now go into some examples where I show you how you can verify certain aspects of correctness of your program at compile time in Swift, and how you can also leverage types as part of your code documentation. First, I'd like to dive into an example, and that is asynchronous error handling. If you've written any iOS app before, you very likely had to deal with asynchronous code that has some sort of callback block, and usually it involves some kind of operation that goes to the network. So you might deal with a callback block in Objective-C that when you import it to Swift would look like this. It is an asynchronous operation that returns some data, and it also potentially can return an error. That's a type signature you work with in Objective-C a lot. What you don't see in Objective-C is that both types here are actually optional. Since everything in Objective-C can be nil, we have to treat everything as an optional, and we have to check every presence of either of the two values. And unfortunately, this means that we have 4 possible combinations. Maybe we have data, maybe we have no data, and with both cases we can have an error or not. And this is actually notoriously difficult to handle, and only after 2 years of writing Objective-C, I found a guide that actually has the COCO guidelines on how to do this correctly. And when you deal with such a pattern where you can get an error, but you can also get a result, the correct way to handle that is always check for the result first. Don't check for the error. And I did this wrong for 2 years because it's buried somewhere in the documentation. It's not part of the compiler. No one warns me about it. But if you handle the error first and then branch out, if you have an error, then you might be discarding a result that is valid. So in this way, Objective-C relies a lot on convention. It's really difficult to know all these rules and to get them right. You need experienced developers that review your code to avoid these issues. So we can do a little bit better in Swift. If you've written a lot of Swift, you might have seen the result type before. And the goal of the result type is really to indicate the success or the failure of an operation in a mutually exclusive way. We can only have one or the other, but never both. And because the result type is implemented as an enum that has an associated value, the compiler even guides us into the right construct of how to deal with this, which is a switch statement. So now we have a nice switch statement where we can switch over the success and the failure case, and the compiler almost forces us to handle both. And that's a big, big improvement over Objective-C. In Objective-C, most developers would either not know about the paradigm that I just mentioned, where we should check for the result and not the error, and often they would also just ignore the error pointer, pass in nil, not do error handling. By using a result type, we can actually force the developer to handle this type correctly, and we express exactly there can either be a success case with some associated data or an error with a certain type. And if you dug a little bit deeper after using the result type, then you would have noticed that the optional type is actually very similar to the result type. They have almost the same type signature. They both have 2 cases. The only difference is that the result has 2 associated values with their cases, and the optional type only has 1. But a more general pattern here is the usage of enums with associated values. And in other languages, they're known as tagged unions. So this is a concept that is available in a lot of languages that have a rich type system. And the goal of this type is to express there are 5 or 6 or however many different values you want to express, but only one of them can be available at any given time. And once you know that this is not syntactic sugar provided by the language, but actually something you can build yourself, you'll run into a lot of use cases where you see you have modeled it incorrectly before, but now with Swift you can actually build an enum, and you can model exactly what you try to express inside of your program. So it's a very useful tool. Let's talk about the next tool that I see a lot in Swift, and that is type aliasing. The problem that type aliasing tries to solve is that we like to use types in Swift to document our program, but in many cases we have types that are used redundantly in many different places. A notorious example is the string type. I've got this great tweet that I could luckily retrieve from my timeline. And that's the year is 2024, and only one type remains, and that is string. We all know as programmers, almost every type can be represented as a string, whether or not it makes sense, but we do it very often. We have an email address that might be a string. We have a phone number that might be represented as a string if it has certain special characters. There are a lot of different ways to use strings. And if we try to rely on the types as documentation, then we lose a lot of value when we use these string types because we don't know what kind of string we're actually working with. We don't know if there may be certain validations that should happen. For example, if it's an email address, we might expect a very specific string, but not an arbitrary string. So you can work around this pretty easily by using type aliases. In a second, I'll talk about a better approach, but this is a fairly easy one. So assume we have a person, and the person has both an email address and a physical postal address. These are two very different types in many regards. So we want to indicate that to the type system so that developers, when they see these types, understand what we expect as input values. So we can use a type alias, and we can say an address is a string, and also an email is a string. And now we can use these type aliases instead of the original type. And this adds some improvement in terms of documentation. And it's really relevant in places where we don't describe the type further, for example, like in return value. If you have a return type, then there's no further documentation about what type you're returning. So having an address or an email address instead of a string is helpful. But this here actually doesn't create a new type. It just creates a new name for an existing type. So it still leaves a lot of room for error. If you want to create a person with an email address, someone can still pass in any arbitrary string, and the compiler will not prevent that. So typically I like to go one step further and create wrapper types. So I might create a struct that actually represents an email, and this is an entirely new type. And this email type now wraps the type that actually stores the underlying value. The email address is obviously still stored as a string, but it's now contained in a separate type that we can use and pass around to improve the type safety and documentation of our code. So now when I want to create an email address, I create an email address by passing in a string. And we can take that another step further. A lot of types actually have, especially a lot of string types, have additional constraints. Not every email address, not every string is a valid email address. And now we can actually encode this inside of this type using a little trick. We can create an initializer that takes the underlying type, which is a string, but it also throws. And if this string is not a valid email address, then we reject this type and we don't create a value of it. And that means whoever has the ability to create a value of type email has actually proven that a string inside of this email is a valid email address. So this value now carries around this guarantee that we have encoded. And it's such a useful concept that I used over and over again that I decided to wrap it into a very small library called validated. What that library does, it basically makes it a little bit easier to create these new types and combine them with validations. The way you can do that is you can create a validated type, and it takes two generic type arguments. The first one is the underlying storage, which in case of an email is a string. And the second type is the validator. And this is just a static type, a type that provides a static function that validates the input and returns a Boolean value, whether it's true or false, that a validation was passed. And then, using this type, you can now create an email address, and you can verify that whenever you have a value of type email, you actually have a valid email. And that is really useful because you push this information into the type system, and you don't have to validate it all over the place in your code. So type aliases are a good tool if you want to improve the documentation of your code and make your types really describe what your program wants to do. But wrapper types are even better because they leverage the type system in that you actually create a new type, and you can even create validations on top of these types. Another useful tool that I learned about last year are phantom types. And before I go into describing what phantom types are, I want to give you a little example. Inside of the PlanGrid app, we have UUIDs, which are essentially just strings that refer to all the different types of objects that we store. These can be either users or blueprints or drawings on top of our blueprints. So we have a lot of different types that we can point to. In Objective-C, we always just use either strings or NSUIDs to point to these objects. But what I realized is when we have a UID at a certain point in our code, we never really know what that object is pointing to. We just have a string. It could be either pointing to a user or a blueprint. Mostly the context makes it clear, but sometimes it's a little bit confusing. And we can use phantom types to solve this. Phantom types are called phantom types, not because I've got this ghost in here, but because we have this type that has a generic type argument that is actually not used in the implementation of the type itself. So this here is the full type implementation that I just mentioned. It's an object UID. All it does is it stores a string. But it carries around a generic type argument, and the only goal of this type argument is to inform the compiler and the developer what this object is pointing to. So now if I construct a kind of artificial example, where I say I want a current user or I want a current sheet. Then before that, I would have a string or a UID return type, but now I have a return type of object UID that is generic over the type that the object is pointing to. So I've again introduced more information into the type system, more documentation, and I also have avoided issues where I can no longer pass in a pointer to a user where I expect a pointer to a sheet. So I've again basically enhanced how much I can express inside of the type system, which reduces a lot of potential errors. So I hope these examples were convincing by itself, but I want to also wrap them together in kind of a bigger case study that shows how we can use these tools and actually get a significant improvement in our type interfaces and in the code that we write. So the example that I want to do is I want to take JSON in memory, so it can either be an array or a dictionary, and I want to turn it into a JSON string, so the text representation. And in Objective-C, the interface for that would look somewhat like this. We have an NS string return type that is a JSON string, and the input type is an ID. The input type has to be ID because an NS array or an NS dictionary are both valid top-level objects for a JSON object. And there's no other common parent except ID in Objective-C. So typically you implement it like this. And throughout the next slides, I don't want to talk about the implementation of this, but only about the type interfaces. Underlyingly, we're going to use NS JSON serialization to take in the object and actually turn it into data, and then turn it into a string. So you start out with this type interface in Objective-C, but it has a lot of problems, because if you look at the documentation for NS JSON serialization, you actually cannot pass in ID, which is any object, but actually the objects that you pass into NS JSON serialization to encode a JSON object have a lot of requirements. The first one is the top-level object has to be an array or a dictionary. The second one is all instances have to be strings, numbers, arrays, dictionaries, or null. All dictionary keys have to be NS string, and numbers are not allowed to be not a number or infinity. All of this here is only documented inside of the documentation that is part of the source code, but is not anywhere in the type system. And I think with Swift we can do a lot better. So let's break it down step by step. The top-level object should be an array or a dictionary. And here we can use a tool that I mentioned right in the beginning. It's an enum with associated values, where you can express the mutual exclusivity of two different cases. We either have a dictionary of type JSON dictionary, which is a type alias that I'll define later, or we have an array of type JSON array. And already we've encoded the first rule inside of the type system. The second rule is that all objects are strings, numbers, arrays, dictionaries, or NS null. Now there are various ways to implement this. The way that I chose is to use an empty protocol that serves as a marker to mark all types that can actually be encoded in JSON. So we can take our JSON root that we just defined and mark it as a JSON value. And additionally, we mark NS string and NS number as valid JSON values. I'm skipping over NS null because we no longer need it in Swift because you can actually have optional values. NS null was only used in Objective-C to work around the issue that you cannot place nil inside of a dictionary or array. So NS null can be skipped. The third rule, all dictionary keys are instances of NS string. This one is pretty easy. We can just say the key is a string and the value in the dictionary is an optional JSON value. And in a JSON array, we just have an array of JSON values. At this point, we've encoded most of the rules inside of the type system. There's one left. Numbers are not allowed to be not a number or infinity. This one is a little bit harder to encode. You could do it using a wrapper type, as I showed you earlier, that actually inspects the value at runtime. But we're going to leave that for an exercise for the reader, since I've got a few more slides to go through. But we've already covered 90% of the cases with what I showed you. 90% of the issues that would occur at runtime are now caught at compile time. If someone constructs something that is not valid JSON, that can be not turned into a JSON string, then the compiler will now emit compiler errors. And all of that is just based on this type information that fits on a single slide. Lastly, I want to talk about code design. So what I talked about now was documentation and correctness, which is an important aspect. But using Swift's type system also has fundamentally changed the way I structure my code. One of the most important aspects is how protocols and generics really work beautifully hand in hand. I like to see protocols as capabilities where I can mark different types to be able to participate in a certain action. And then I like to create generic types that can operate on these capabilities. To make it a little bit more concrete, I'm going to show you an example on the next couple of slides. The bigger overall theme is that I've replaced a lot of what is called subtype polymorphism with parametric polymorphism. Sounds very fancy, but what we're doing is we're moving away from subclassing, and we're trying to use generic types instead for code sharing. One concrete example, again, that existed more or less in this way in the PlanGrid app. It's not a 100% example, but it's very similar. If you imagine any app out there, it usually has what I like to call vertical pillars of certain functionality that it has to provide for various types. In the PlanGrid app, one of them is persistence, the other one is downloading, the other one is uploading. These are kind of generic services that a lot of types participate in. But then each of the types has to customize the behavior in some way. A photo is might upload it a little bit different than user information, and the same is true for persistence, where we maybe have a different schema how we store the object in a database. The typical way of dealing with this in Objective-C was usually resorting to inheritance. You would move kind of the common behavior into a parent class called a base data access object or a base downloader, and then you would have specific subclasses for each of the types where they can configure the behavior and adjust it as needed. And it quickly leads to something that I named type explosion, because you have all these vertical pillars, but then for each of them you have one customization. So now you have a photo downloader, a photo persistence object, and you have a lot of types that have often more complexity than they need to have. But another problem with this approach is it's very difficult to separate what should go into the base class and what should go into the subclass. And often a lot of the download functionality will then bleed into the subclass and be repeated over and over again. So you have a lot of types that are really complex, that are all having a lot of behavior, and they're really difficult to modify and maintain. So we moved mostly to a model that looks like this. We have the vertical pillars are now generic types, and our data types just configure the behavior through protocols. So our data types no longer they no longer have subclasses of the downloader or persistence manager, but actually just implement protocols for the customization. And the base types themselves are just generic types. So our data access object is now generic over persistable. Our downloader object is generic over downloadable. So let's put it into a concrete example where I want to build a simple downloader that can do some caching and that can also decode the result and turn it into a value. And I would start out building some protocols to mark these different capabilities. As I said, in this architecture or in this model, I like to think of protocols as things that types can participate in. And each of the protocols provides a certain piece to that generic infrastructure where it basically provides customization hooks. So a downloadable type, for example, might provide an endpoint URL, because the endpoint for a photo or for a user might be different. For a decodable type that can be decoded from data and turned into a value, we provide an initializer that takes in data and creates an instance of itself. And if a type is cacheable, then we might have a different caching duration for each of these different types. So you might want to configure that as well as part of a separate protocol. So protocols provide extension hooks. And now we have these generic types, and I'm going to keep a very simple example to make it fit on these slides. So let's assume we have a download function that is synchronous, that blocks the UI, and that you can pass in an identifier for the object you want to download, and it returns the piece of data once the download completed. So you now would have this generic downloader that has a type T, and it's generic over a downloadable type. And by being generic over downloadable, we now have information about this type T that allows us to access everything that is part of that protocol, of the downloadable protocol. So one part of the downloadable protocol is the endpoint. So our generic downloader can now look at the type and can see which endpoint does it specify, and then can go there and fetch the data. Without that, we have to have a subclass for each of these types. So that's the most simple example. But let's assume we have another type that is also cacheable. So we can now extend this downloader, and we can dynamically check this type and see is t.self maybe a cacheable type. And if it is a cacheable type, then we might perform a different code path, where before we go to the network, we actually check in the cache and retrieve the object from there, and after we got it from the network, we store it in the cache. So we can do this dynamic type check to see if our type that is downloadable is also cacheable, and then perform some different code. And we can also extend the interface of this downloader, only for specific types, using constraint extensions. So if we have a decodable type, then we can say our downloader provides another method that doesn't return data, but it actually returns an instance of type T. And it can do that because we know that decodable provides us with an initializer that takes data and creates an instance. So we can rely on this type information by looking at all the types through protocols, and then relying on the information that these protocols provide us. And the implementation on the photo itself would look pretty straightforward. We maybe have different extensions for all these protocol conformances, and then we just provide the configuration for the downloader. So what is URL, what is the caching duration, how am I initialized from a piece of data? All of these are now just configurations on our data types. And if we tie all of this together, then we get a simple expression like this here, where we have a downloader that is generic over photo, And then when we call download on this type, and we say we want a return type of photo returned, then we now invoke the right method. The downloader will look up the endpoint of the photo, will decode the type, and then return it. So all of this is based on protocols and generics. And the two other concepts that I showed you are safe dynamic type checking, so looking does a type conform to a certain protocol, and then branch off the code and behave slightly differently, or constrained extensions to actually provide a totally different interface for certain types that conform to a protocol. So in general, there's one big theme when we talk about static and dynamic type systems, and we talk about Objective-C and Swift. And that is that at the beginning, when you start writing in a language that has an expressive type system, there's often a lot more effort in expressing your intents because you have to use a more formal language. Instead of using this result block, you have to now use a result type where you say exactly what is the return type, what is the error type. When you want to encode something in JSON, you have to describe exactly which types are involved. What is JSON encodable? You have to create a new protocol. It's a lot of work up front, but it really pays off at scale. I see that in the PlanGrid app. For every type that we introduced, we enrich the information in our program, both for the compiler and for all developers that come after us. And if you have a really big app, then it pays off very quickly. Because there's a lot of issues that get caught at compile time that you wouldn't catch before, and there's a lot more documentation in your code. So to summarize everything, types are really great for documentation. They enable correctness checks at compile time, which reduces both runtime errors, but it also improves the feedback loop. If something gets called at compile time, you actually are more likely to resolve that issue faster than when you have to run the app to detect the issue. And generics also offer a great alternative to subtyping that I've used a lot. I also listed all the concepts down here that I mentioned because I really took a broad brush over a lot of ideas. So if you think any of them are interesting, you can go back to the slide and you can study them in more detail. And that's all I have. Thanks a lot. And I do believe we have some time for questions because I talked fast enough. Except you want to go for lunch. Feel free.
Hey, down the front, Ben.
Oh.
Oh, over here.
Nice.
Great talk, really enjoyed it. Love using types wherever I can. One of the things that I'm not entirely convinced about, though, is your use of throws in an initializer. I'm wondering if you could just elaborate on why you think that's a beneficial pattern to be following.
Yeah. So the idea of throws in initializer is that you have to guarantee as soon as you have a value that it has passed this correctness check. If you don't, you basically push that to the point where the value is constructed, which is usually just one single place. But the value is used in a lot of different places. So if you don't verify that construction, then you have to verify that usage. And it's usually used much more often than it is constructed. And also, usually when you construct it, you can give valuable feedback. In most cases, it would be a user input or something like that. So you would actually want to tell the user it failed. And so these are the two main benefits, really. You get the feedback there where the error occurred, and you get the validation in one place instead of checking it at all usage points. Does it answer the question?
Yeah. A follow-up is, why not use result then?
As part of the initializer?
Or as like a function that does the creation and validation?
It's a good point. I don't really know where I stand on throws versus result type in general yet, but if I had a validation that was really complex, then I would definitely refer to that. If it's something really simple, like an email address, where it's like either it's a correct one or not, there are not a lot of failure cases, then I would do this. And otherwise, I probably would use a result type, or maybe even another enum that has 5 or 6 different failure cases. But yeah, it's a good point. Any more questions? Okay, we can have lunch. Thanks a lot.
Thank you, Ben. Thanks.